Hello. Good evening. Okay. We'll start with fields today. Of course, I've already defined what a field is. From our perspective, a field is nothing but a ring in which all the non-zero elements have a multiplicative inverse. So we won't list all the, if uh, you had to define a field independently, you would have to list all the properties of a ring and then add the additional condition that all non-zero elements are units. So that is a field. And one field we saw was the field of rational numbers, which is set of all numbers of the form m by n, where m and n are integers, n is not the zero element. Here you can see that z is not a field, but it is contained in the set of rational numbers. So each integer can be considered as that integer divided by 1. So each integer is a rational number. Z is a ring, and from that ring we got a field by allowing fractions to exist. So this process can be generalized to any integral domain R. An integral domain is a ring in which the product of two elements is zero if and only if one of the elements is zero. So matrices won't be an integral domain because two non-zero matrices can give you a zero matrix. So something like the integers, where if you multiply two non-zero integers, you will get a non-zero integer. And if the product of two integers is zero, one of them must have been zero. Something like that is called an integral domain. How we constructed the rationals from the integers, the same way we can construct the field of fractions from any integral domain. So we construct for any integral domain, we can construct a field K which contains R, and we define K to be set of all elements of the form A by B. It doesn't mean that we are dividing A by B. It is simply a notation. In the case of integers, it corresponds to the, it is similar to the division operation, or it is similar to, it's simply a fraction, that's all. A and B are elements in the ring, and B is not the additive identity of the ring. On this, on this set of elements, we will define, for a ring we need what? We need two operations. So we'll define the addition and multiplication. Addition would be, you have two elements A by B plus and C by D. If you add them, you get AD plus BC divided by BD. And since R is a ring, AD is a ring element by closure, BC is a ring element by closure. So AD plus BC is also a ring element. And since R is an integral domain, and we have said K is set of all elements of the form A by B where the denominator is not zero. So B is not zero and D is not zero. Since R is an integral domain, BD will not be zero. So the sum is also a fraction of two ring elements where the denominator is not zero. Multiplication is defined as A by B into C by D is equal to AC by BD. Now there is one problem here. Can you identify what the problem could be? Just with the definition of addition and multiplication. Can you take a guess? No, just with this definition of addition or multiplication. Just the three definitions I have given here. So suppose you add 1 by 2 plus 3 by 5. What will you get? You will get, by this definition, 5 plus 6, 11 divided by 10. Suppose you add 2 by 4 plus 9 by 15. What will you get? 30 plus 36, 66 divided by 60. These seem to be two different numbers, but you can, since these are rational numbers, you can cancel out the common factors and write this is also equal to, you cancel out 6 in both the numerator and denominator, write this as 11 by 10. You can do that in integers and rational numbers. But what is the guarantee that you can do that in an arbitrary ring? So here you factorize this, right? You wrote this as 66 by 60, you wrote this as 6 into 11 by 6 into 10, and then we cancel out the 6, right? And we say that 11, this is equal to 11 by 10. They are the same thing. So that is because 2 by 4 was the same as half in rational numbers. 9 by 15 is the same as 3 by 5. So we actually added the same numbers with different multipliers. So in the end, what you got was equivalent to 11 by 10. These types of things make sense here, 6 into 11 factorization, that you can do because they are actually numbers. But the way I have defined K, it is with any arbitrary ring, any arbitrary integral domain. But for any arbitrary integral domain, what is this notion of factorization? There might not be a notion of factorization at all. And, and there might not be any notion of cancelling. So this division notion might not make sense there. And even here, this is kind of ambiguous. When I say this is numbers of the form A by B where A and B are ring elements, nowhere does it say that half is the same as 2 by 4. So this is not a good definition of things. Um, because we want half to be same as 2 by 4. It's the same fraction of something, right? Half of something is the same as 2/4 of something, which is the same as 3/6 of something. So we want these things to be equal, and in rational numbers they are equal. We do say that half is equal to 2 by 4. So that is okay when it comes to numbers, but here the definition I given for k and with addition and multiplication, nowhere do I say this type of thing is possible. That if A and B are different, they can still be the same element. Something like half is the same as 2 by 4. I need that kind of notion also if I want to do this. Otherwise, it will simply not make any sense for us generally. So what we do is I will go into a small deviation. We'll keep this as is for now, and we'll define this more formally. So let's see. Let D be an integral domain. So you'll have to hammer into your brain the notion of an integral domain. It is simply a ring in which the product of two non-zero elements is non-zero. And the only way to get a zero product, the product of the two elements to be zero, is if one of the elements is zero. So let D be an integral domain. Define the relation on D cross D. You know what D cross D is, right? The Cartesian product. A set of all ordered pairs in which first element and second element both are from D, except the element 0, comma 0. So we don't want a 0 by 0 form. That's why we are excluding elements of the form 0, comma 0. We define the relationship by the rule A, comma B is related to C, comma D if and only if AD is equal to BC. This forms an equivalence relation. This is the lemma. Can you prove this? AB is equal to AB. So this is actually our D and this is actually our C. Yeah, so due to we are looking at in our rings, the multiplication is commutative. So we said it's an integral domain. So here also multiplication is commutative. So AB equal to BA. That is, we are replacing D by B and C by A. In that case, if AD equals BC, we have AB is related to CD. So AB is related to AB. So that is reflexive. Then, like you said, okay, there is one other thing here. So here, if you have AB is related to C comma 0 for some element, that is actually I am writing in ordered pair form, but you could write it like this. Then that would mean that A into 0 is equal to B into C or BC is equal to 0. But C is, I'm saying this is C comma 0 where C is non-zero. Okay. Because 0 comma 0 is not allowed. We have excluded 0 comma 0 here. So if one of them is 0, the other must be non-zero. So C is not 0. But since it is an integral domain, B must be equal to 0. That means this must be 0. So A by 0 is in fact related to B by 0 for any A and B. But what that means is that if actually what we do is we discard these numbers when we are dealing with fractions. We say that denominator has to be non-zero. Even if you don't consider that, you can still use it in this form. Uh, a number with a denominator 0 is only related to other numbers with denominator 0. We only exclude 0 by 0. So that does not cause any issues for us. Okay, and if AB, we have AB is equal to AB, so this is actually in place of D. For symmetry, we need to show that AB is related to BA. That is true if Sorry. Yes. If AB is related to CD, then CD is related to AB. That's what we have to show. But if AB is related to CD, then AD equals BC. But we can also write this as CB equals DA. What this implies, Mhm. So this implies CD is related to AB. So that shows symmetry. And then if AB related to CD and CD related to EF, then AD equals BC and CF equals DE. That means ADE equals BCE. How do we get? We need AB is related to EF. So we need AF is equal to BE. So you can write A, since AD equals BC, you can write ADF is equal to BCF. But CF is equal to DE, so you can write ADF is equal to BDE. But in that case, since if D is 0, then B, like I showed earlier, B must also be 0 and then F must also be 0. So in that case, A comma 0 is always related to E comma 0. So AB is related to EF directly. If D is not 0, we can cancel out D here. AF is equal to BE, which would mean that AB is related to EF. So that is transitivity. So the relation A comma B is related to C comma D if and only if AD is equal to BC is an equivalence relation. Yes. Now what we do is we will denote the equivalence class containing some element A comma B by A divided by B. So this A by B is actually notation for the equivalence class containing A comma B. And then we'll denote, we'll say K. We'll also call it the frac of B. Is A by B, set of all A by B, where A comma B belong to the integral domain, and B is not zero. Can you understand the difference now? Yes. So in modular arithmetic also we had Z mod NZ, no, where yeah we treated a number, we had it was a set of equivalence classes, but we actually treated it like numbers themselves. We treated it the same as Zn, right? Yeah, because they were isomorphic. So instead of always writing the equivalence class containing 0, equivalence class containing 1, we kind of treated it as 0 and 1 and said that we'll simply do mod n arithmetic when we are multiplying or adding. And everything worked out there. So this is kind of a similar thing. So instead of working with fractions of these numbers directly, we are working with the equivalence classes of fractions. So in this case, the equivalence class containing so here D is an integral domain, but if we took that to be the set of integers, then the set of rational numbers would really be towards the equivalence class of all the fractions. So in that sense, half 1 by 2 is actually the equivalence class containing 1 comma 2, which would also contain 2 comma 4. So the equivalence class containing 1 comma 2 is the same as the equivalence class containing 2 comma 4. And 1 by 2 and 2 by 4 are simply notations to denote those equivalence classes. So 1 by 2 would be the same as 2 by 4. They are the same equivalence class. So if you remember in the preliminaries when we were discussing equivalence classes, uh, the equivalence class of an element is a set of all elements related to it. Okay, this is how set of all x such that x related to A. Yeah, suppose B was related to A, B belonged to the equivalence class of A. Then you could also call this the equivalence class of B. That would be the same, right? Yes. And what I'm saying is, you could call the equivalence class by any name, by picking any element within the equivalence class. Yes. So this A and B, these were simply representatives for the equivalence class. When we talked about equivalence classes, it's actually a set of elements. But just to denote the set of elements, we would pick one element from the set and say it is the equivalence class containing that element, because we know that each element can only be part of one equivalence class, can be in two equivalence class. So just by telling you one element in an equivalence class, I would be telling you which equivalence class I am talking about, which set I am talking about, right? So these A, B, and all were the representatives for the equivalence class. So you could pick any element in an equivalence class to represent that equivalence class. So that means if I had that the equivalence class of the remainder when you divide by 3, say we had 0 bar, 1 bar, 2 bar. That is, this is a set of all elements which give remainder 1 when divided by 3. This is a set of all elements which give the remainder 2 when divided by 3. This is a set of all elements which gave you 0 when divided by 3. This was also equal to 3 bar. This is also equal to 6 bars. So this representative, you could pick any of the elements in that particular set equivalence class. Here this is equal to 4 bar, 7 bar. This was 5 bar or 8 bar. They're the same equivalence class. You are just changing the representative. And then when we did addition, when we said 1 bar plus 2 bar, this is equal to equivalence class containing 1 plus 2 mod 3. That is, plus 2 mod 3 is 0. Now, instead of 1 bar or 2 bar, if you take 7 bar plus 8 bar, you should get the same thing because 1 and 7 are simply the representatives. What you are actually adding are the equivalence classes, the sets as an element. So, by picking a different representative, we are not picking a different class. The addition of two classes shouldn't change if you change the representative element because representative element is just there to tell you which equivalence class you are looking at. So 7 bar plus 8 bar, it should be 15 bar, 15 mod 3 bar. But 15 mod 3 is also 0. So this also gave you 0 bar. So in the same way here, half is actually, and when I say half, actually mean when I say A by B, actually mean the equivalence class containing half. Yes, you can also write this 2 by 4, 3 by 6, 4 by 8, all of them. So when we did half plus 3 by 5 and got 11 by 10, this is the same as this is equivalent to 2 by 4. What you're actually adding is the equivalence classes. So the representative doesn't matter. Here we have 6 by 10. Or it 6 by 10? So 9 by 15. And you had 66 by 60. But now, even without a no, without any division or factorization, how do you say these two are equal? Well, the equivalence class containing 11 by 10 is equal to 66 by 60. These two are equal because 11 into 60 is equal to 10 into 66. So that's how we say two elements are related, right? A by AB it's related to CD if AD is equal to BC. So we can know that 66 by 60 is in the same equivalence class, is related to 66 by the equivalence class containing 66 by 60 is the same as the equivalence class containing 11 by 10 if 11 by 10 and 66 by 60 are related. And that is true because 11 into 60 is equal to 66 into 10. Right? This gives you a way of telling when two equivalence classes are the same. Now we have defined this frat D, the set of equivalence classes of the relation A comma B is related to C comma D if and only if A D is equal to B C. That is the relation. So this actually you can write as equivalence classes of elements like this, but we are using this notation. I mean, this is simply notation. A by B is simply the equivalence class containing the ordered pair A comma B. That is clear, right? Now what we have to do is the next lemma is we'll define the addition. Let D be an integral domain. We define two operations on track B called addition and multiplication by the formula A by B plus C by D is AD plus BC by BD, and A by B into C by D is AC by BD. So note here that you're actually adding two equivalence classes. A by B is simply the notation for the equivalence classes and equivalence class containing AB, A comma B. C by D is simply notation for the equivalence class containing the element C comma D. And here also you are multiplying two equivalence classes. We are saying that if you multiply two equivalence classes of this form, you will end up with an equivalence class containing this element. And the lemma is that these are well-defined operations. By that we mean that in the previous we had that example, right? So instead of adding half and 3 by 5, you added equal some other representative, 2 by 4 and 6 by 10. The end result you get, whatever you get, this will be same because you are actually adding the same equivalence classes with different representatives. That's it. Half and 2 by 4 are different representatives of the same equivalence class. 3 by 5 and 6 by 10 belong to the same equivalence class. So instead of 3 by 5, if you plug in some other number in the equivalence class, and instead of half, if you plug in some other number in the equivalence class, and you get some result, at the end of the day, those two results will belong to the same equivalence class. So this addition actually works because regardless of what, it is well defined because it does not depend on the representative that you pick. So it does not depend whether you pick half or 2 by 4 to denote the equivalence class containing half. The sum will be the same. That's what it means by well defined. Furthermore, A by B is equal to AC by BC. This is also equal to A by B into C by C. This part is simply by definition. A by B into C by D is equal to AC by BD. So A by B into C by C is equal to AC by BC. But this part we have to show. AC by BC is equal to A by B. That is, you can cancel out this common factor. And for any c not equal to 0, okay, this is for any c not equal to 0, and a plus d by b is equal to a by b plus d by b. So here these two things, we are looking at them from the perspective of equivalence classes. So the equivalence class containing a comma b is the same as the equivalence class containing ac comma bc, and the equivalence class containing a plus d comma b the same as the equivalence class containing a comma b plus the equivalence class containing d by d comma b. That's what it means. So here we are trying to get rid of our dependence on the common factorization and division that we have in integers, and trying to generalize these notions for an arbitrary integral domain. So this is true for integers, right? You can cancel out the common factor. We are saying if you define these things to be equivalence classes instead of simply um, a fraction, it's actually the equivalence class of all fractions that uh, depend by that relation that we had in the beginning. Then you can also write this. So how do you show that it is well defined? In any question similar to this, how would you show that it is well defined, or that the operation is well defined? So I will give you an example. Suppose you have a function f of the function on is a two vari the function on rational numbers. F of a by b is equal to 2 power a plus b. Would this be well defined? F of half is 2 power 3, which is 8. F of 2 by 4 is 2 power 6, which is 64. But 8 is not 64. But in our notion, half is the same as 2 by 4. So this function well defined. Yes, so yeah. So it should not depend on whether I am picking half or whether I am picking 2 by 4. It should not depend on the representative I am picking. This is a function on the equivalence class. So it should depend only on the equivalence class that I picked, not on what representative I am using to represent the equivalence class. Shouldn't change based on that. So if addition is well defined, let's say I pick two elements from two different equivalence classes. Let's say I pick the element a by b and c by d. and these belong to rack B. Suppose A prime by B prime is equal to A by B, and C prime by D prime is equal to C by D. To show left hand into are well defined, we have to show A prime by B prime plus C prime by D prime is equal to A by B plus C by D, because A by B was equal to A prime by B prime and C by D was equal to C prime by D prime. We have to show this. That is, so this would be what? A prime by B prime plus C prime by D prime is A prime D prime plus B prime C prime divided by B prime D prime. We have to show this is equal to AD plus BC by BD. But what does it mean to be equal? What is the criterion? Yeah. Then these two are related, so they are the same. These two elements are related, so they are actually representing the same equivalence class. So we have to show this. Uh, but we already know that since A prime B prime A prime by B prime is equal to A by B, A prime B is equal to A B prime, and C prime D is equal to C D prime. This we already have. So consider AD plus BC into B prime D prime. This is equal to AB prime into DD prime plus BC into B prime D prime can be written as BB prime into CD prime. Simply distributivity I have used and rearrange the terms. Then this is AB prime is equal to A prime B from here to DD prime plus CD prime is equal to C prime D from here. So this can be written BB prime to C prime D. Next again I will rearrange. I'll write A prime D prime into BD, and here I will write B prime C prime into BD. This is nothing but A prime D prime plus B prime C prime into BD, which is our LHS. So we have shown this. So addition is a well-defined operation when you consider this addition of equivalence classes. The result does not change when you change the representative for your equivalence class. So multiplication is well defined if A by B into C by D is equal to A prime by B prime into C prime by D prime. That is AD into B prime D prime is equal to BD into A prime C prime. But we know that A prime B is equal to AB prime and C prime D is equal to CD prime. So This was AC. So AC into B prime D prime can be written as AB prime into CD prime. This can be written as A prime B into C prime D. Again, this can be rearranged as BD into A prime C prime, which is the right hand side. So multiplication is also well defined. Now we have a well defined set, the equivalence class of the relation. Equivalence classes of the relation AB is related to CD if AD is equal to BC. With addition of equivalence classes defined as A by B plus C by D is equal to AD plus BC by BD. And multiplication of equivalence classes defined as A by B into C by D is equal to AC by BD. Now we have all the elements. We have formally clearly defined without any ambiguity and with well-defined operations, addition and multiplication. We have defined the set frac D with plus and into. So now finally we can show that this is actually a field. So the theorem is the main theorem of this lecture, that D be an integral domain. Then frac D is a field such that D is actually a subring of frac D when D is identified with elements of the form A by 1, where A belongs to D. So analogous to um, the set of rational numbers Q is a field where Z is a subring of Q, and an integer 2 can also be written as the rational number 2 by 1. In that sense, 2 is actually each integer is contained in the set of rational numbers. Okay, actually, let us stop here. This is the theorem that this field of this set of fractions that we have defined, the equivalence class of fractions, is actually a field. We will see the proof in the next class. Subring. We also use it for subgroup also. But here, since we are dealing with rings, we use it for subrings. Okay, I keep forgetting about the notes. I'll upload it. I'll upload by tomorrow, before tomorrow's class. Ah, yes. Today I forgot that we have changed the timings. I only realized when you sent the email. No. Yes, yes. Ah, okay, bye.